If you track the carbon management space, uh, you are probably pretty familiar with the constant debate over what we actually do with captured carbon dioxide.
Right, because injecting it underground is sort of the standard model.
Yeah, exactly. But building a massive global infrastructure just to bury a waste product, I mean, that's a tough economic sell.
It really is. It's an expense with no real product at the end.
But what if we could intercept that carbon and feed it directly into the supply chain for advanced materials? What if defossilizing the chemical industry is actually our most viable pathway to gigaton-scale carbon dioxide removal?
That is the exact mission we are exploring for you today.
Today, we are looking at the paper titled Techno-Economic Assessment of Electricity-Based Graphene Production from Atmospheric Carbon Dioxide as a Potential Negative Emission Option.
It's just a highly compelling piece of techno-economic modeling. This study moves the conversation past the theoretical physics of carbon capture.
Right, getting into the real-world numbers.
Exactly. It forces us to look at the hard operational expenses, capital expenditures, and the market viability of actively reversing emissions while manufacturing a high-demand commodity.
And we all know the climate math we're up against here.
Oh, absolutely.
To hit the Paris Agreement's 1.5 degrees Celsius target, mitigation and emission cuts are, well, they're no longer mathematically sufficient. We've already overloaded the atmosphere.
Yeah, and if we look at the even safer 1.0 degrees Celsius target, which brings us back to those safe planetary boundaries of roughly 350 parts per million of atmospheric CO2, the need for engineered carbon dioxide removal, or CDR, becomes colossal.
We're talking gigatons, right?
More than that, we are looking at a requirement to remove up to 1,750 gigatons of CO2 by the end of the century.
1750 gigatons.
Yeah.
That is hard to even picture.
Right. That scale of atmospheric scrubbing requires industrial solutions that can actually sustain themselves economically.
Which brings us to graphene.
Yes, the wonder material.
Anyone following materials science knows graphene's structural reputation. You know, the two-dimensional hexagonal lattice, the immense tensile strength, the unmatched thermal and electrical conductivity.
It's an incredible material.
It's highly valued, but currently, the carbon used to manufacture it is overwhelmingly derived from fossil fuels.
What's fascinating here is the elemental bridge this study builds between the climate crisis and the advanced manufacturing sector.
How so?
Well, graphene, depending on the application, requires up to 99% pure carbon.
Okay.
This study bypasses the fossil fuel supply chain entirely and asks, what are the economics of sourcing that high-purity carbon directly from atmospheric CO2?
Oh, wow. So you're basically pulling the building blocks right out of the sky.
Precisely. It effectively merges carbon capture, utilization, and sequestration, CCUS, into a single monetizable industrial loop.
Okay, let's unpack this. Moving from ambient CO2 to a synthesized commercial-grade graphene sheet requires a highly integrated defossilized value chain.
It's a very specific operational sequence.
Right. The study models a sequence that starts with direct air capture to isolate the CO2.
Yes, DSC is step one.
But to synthesize the hydrocarbon precursor needed for graphene production, specifically methane, we also need a massive input of green hydrogen.
The model couples the direct air capture facilities with standard PEM water electrolysis to generate that hydrogen.
Got it. So you've got the captured CO2 and the electrolytic hydrogen.
Exactly. And once you have those, you feed them into a methanation reactor.
And that gives us the methane.
Right. That synthetic methane, CH4, then becomes the clean, carbon-rich precursor gas that gets fed into the graphene synthesis equipment.
My immediate thought when looking at that chain is the staggering grid load.
It is significant.
PEM electrolyzers alone are notorious energy hogs, not to mention the thermal and electrical demands of the DIE sorbents and the methanation process itself.
That's a crucial point.
If a manufacturer powers that whole chain with grid electricity that still has natural gas or coal in the mix, aren't they just emitting more carbon than they capture?
The study makes it abundantly clear that carbon parity is the highest hurdle. If the energy source isn't pristine, the entire negative emission concept completely collapses.
So it has to be perfectly clean energy.
Yes. The life cycle assessment modeled in the study dictates that the entire facility, from the DT fans to the electrolysis stacks to the final synthesis reactors, must be powered by 100% renewable electricity.
Solar, wind, geothermal, or hydro.
Exactly. It is a strict prerequisite.
Okay, assuming a manufacturer can secure that kind of dedicated utility-scale renewable power,
Yeah.
they still have to turn that synthetic methane into graphene.
Right. And the study evaluates two distinct techno-economic routes for this.
Let's look at Route 1, which basically represents the high-end path roll-to-roll chemical vapor deposition, or CVD.
CVD is the industry standard for producing flawless single-layer graphene.
How does it actually work in this context?
You're essentially introducing the methane gas into a high-temperature environment where it decomposes. The carbon atoms then deposit themselves in a perfect atomic lattice onto a continuously moving catalytic substrate.
Usually copper foil, right?
Typically copper foil, yes. Because the atomic structure is so highly ordered, CVD graphene is the premium material required for high-tech applications.
Like transparent electrodes and advanced photovoltaics.
Exactly, and next-generation semiconductors.
The thermal budget for that process is brutal, though. The study notes the CVD furnace requires a constant operating temperature of 1,000 degrees Celsius.
It's intensely hot.
I can't even fathom the operational expenditure of maintaining that kind of thermal environment, 247,
Oh,
let alone the capital expenditure for this specialized high-temperature alloys and continuous roll-to-roll machinery.
the energy intensity is precisely why the economics of Route 1 are so precarious.
Precarious is putting it mildly.
The study's model reveals that to make CVD remotely viable, the manufacturer absolutely must incorporate a rigorous recycling loop for the copper foil substrate.
Because mining new copper is incredibly energy-intensive.
Right. They base their projections on a strict 95% copper recycling rate.
95%.
Yes. Without that, the energy required to continuously mine, smelt, and pre-clean new copper would shatter any hope of a net negative carbon footprint.
But even factoring in that 95% recycling efficiency and projecting technological advancements out to the year 2050, the specific energy consumption is still massive.
It is.
The study calculates it will require 80.3 kilowatt hours of electricity to produce a single kilogram of CVD graphene.
And when you translate that 80.3 kilowatt hours into operational costs, alongside the equipment depreciation and labor, the 2050 projections put the production cost of CVD graphene at 89.5 euros per kilogram.
Almost 90 euros for a single kilo. Can a commercial materials company actually survive on those margins?
In the premium electronics market, yeah.
Because they can charge a premium for the perfection.
Exactly. The study notes that high-quality single-layer CVD graphene can command a minimum selling price of 98.4 euros per kilogram.
So that leaves a profit margin of roughly 9.7 euros per kilogram.
Purely as a business model for a niche, high-tech supplier, it is solvent.
But we have to evaluate this against the original mission gigaton scale carbon dioxide removal.
Right, the climate perspective.
If we are relying on Route 1 to scrub the atmosphere, how do those economics look?
They look entirely unfeasible for bulk climate intervention.
Let's hear the numbers.
When you divide the total net carbon removed by the immense costs of the CVD process, the effective cost of carbon removal is an astronomical 24,402 euros per ton of CO2.
24,000 euros for a single ton.
It's staggeringly high.
Given that the current voluntary carbon markets are fighting over engineered removal credits priced in the hundreds of dollars, no government or corporation is going to subsidize a 24,000 euro ton.
Not a chance.
Route 1 might secure a sustainable supply chain for the semiconductor industry, but it fails as a scalable climate solution.
It is simply too slow, too energy hungry, and far too expensive to serve as a primary CDR mechanism.
Here's where it gets really interesting. The study anticipates that bottleneck and introduces a second manufacturing pathway that completely changes the techno-economic outlook.
Yes, Route 2.
Route 2 is electron beam plasma methane pyrolysis, or EBPM.
EBPM bypasses the continual substrates and massive thermal gradients of CVD entirely.
So no 1,000-degree furnace.
Exactly. Instead of slowly growing a lattice on copper inside a furnace, EBPM utilizes a high-energy electron beam to generate a plasma state.
Okay, plasma.
This plasma directly ionizes the synthetic methane gas. It forcibly cracks the carbon-hydrogen bonds, splitting the methane molecule into solid carbon flakes.
Which is our bulk graphene.
Right. Solid carbon flakes and a stream of pure hydrogen gas.
It sounds significantly less complex from an engineering standpoint. You aren't managing the delicate spooling of copper foil or dealing with the heavy capital expenditure of immense vacuum furnaces.
It is much leaner.
But what really stood out in the study's operational model for EBPM is how it handles that hydrogen byproduct.
The internal recycling loop. It is arguably the most elegant engineering feature in the entire process.
Tell us about it.
Remember that the methanation step at the beginning of the chain requires massive amounts of hydrogen, which is typically supplied by those energy-intensive PE electrolyzers.
Right, the water splitters.
In the EBPM route, the highly pure hydrogen generated from cracking the methane is captured and routed directly back to the methanation reactor.
Oh, that's brilliant. You're effectively short-circuiting the most energy-intensive part of the supply chain.
Exactly. By feeding the hydrogen back to the start, you drastically reduce the required capacity and runtime of the water electrolyzers.
And I imagine the reduction in electrolyzer workload has a cascading effect on the entire facility's energy profile.
A massive effect. The study models that by 2050, the EBPM process will only require 47.9 kilowatt hours of electricity per kilogram of graphene produced.
That is a steep drop from the 80.3 kilowatt hours demanded by the CVD route.
Almost half.
And I imagine the capital expenditures are noticeably lower as well, given the lack of substrate handling and lower thermal requirements.
Substantially lower.
So how does that hit the bottom line?
When you combine the reduced capex of the plasma equipment with the drastic reduction in OPEX from the lowered electricity demand, the total production cost drops off a cliff.
Down to what?
The study projects the cost of EBPM graphene to hit 1.35 euros per kilogram by 2050.
Wait, from nearly 90 euros down to $1.35.
Yes, 1.35 euros.
That kind of precipitous drop in manufacturing costs usually implies a severe compromise. What is the catch here? Are we sacrificing structural integrity or electrical properties?
You are sacrificing the perfect atomic structure.
Okay.
EBPM does not produce pristine single-layer sheets. It produces bulk graphene flakes, which means it has more chaotic morphology and slightly more defects.
So you can't use it for phone screens.
Right. You cannot use EBPM graphene to build a transparent smartphone display or a microscopic transistor.
But it changes the math on the carbon dioxide removal cost, doesn't it? If the production cost is only 1.35 euros per kilo, what does that do to the CDR pricing?
It pushes the technology into the realm of true global viability.
You mean the number?
The study calculates that by 2050, the carbon removal cost via the EBPM route drops to a highly attractive 369 euros per ton of CO2.
369 euros.
Yes.
We went from 24,000 down to a number that actually competes with projections for standard direct air capture and sequestration.
Exactly.
Only in the scenario, you aren't just burying the carbon in a hole, you have a highly conductive bulk material to sell.
It completely flips the incentive structure. At 369 euros per ton, companies aren't just performing a planetary cleanup service at a loss.
They're a manufacturing business.
Right. They are manufacturing a scalable commodity that can offset the costs of the capture infrastructure.
So what does this all mean? If EBPM gives us a cheap bulk supply of slightly imperfect graphene flakes, where's the market demand for that?
That's the billion-dollar question.
Because if it's not going into semiconductors, who is buying millions of tons of this material?
The study targets the energy storage sector, specifically pointing to the limitations of current battery chemistries.
Like EVs?
Exactly. The primary market application for this bulk EBPM graphene is as a replacement for the cathode materials in lithium-ion batteries.
The LFP ones?
Yes, particularly the lithium iron phosphate, or LFP, cathodes that dominate the EV market right now.
LFP batteries are robust and cheap, but they are notorious for their relatively low electrical conductivity and sluggish lithium-ion diffusion rates.
Which is exactly why graphene is the ideal substitute.
Even in flake form.
Yes. Despite being in flake form, EBPM graphene retains exceptional electronic conductivity, a massive surface area, and a planar geometry that facilitates rapid ion transport.
So it upgrades the battery.
Integrating this material into battery cathodes dramatically increases energy density and charge-discharge rates.
The implications for the electric vehicle industry are massive.
Truly transformative.
We are looking at a future where the core components of EV energy storage are manufactured from carbon pulled directly out of the atmosphere. The battery itself becomes a physical vault for sequestered CO2.
And we have to look at the scale of that specific market to understand the climate impact.
Right, how much graphene do we actually need?
The study evaluates the projected global demand for graphene out to the year 2050.
Okay.
As industries pivot toward advanced composites, supercapacitors, and enhanced battery cathodes, the global demand is estimated to reach 700,000 kilotons annually.
700,000 kilotons.
Yes.
If we hypothetically scale up the highly efficient EBPM infrastructure to meet that entire global demand using defossilized air-captured carbon,
Yeah.
what is the net effect on the atmosphere?
The study calculates an astonishing total negative emission potential. Meeting that 2050 demand via this electrified route could result in the removal of 2.57 gigatons of CO2 every single year.
2.57 gigatons. Considering our current global emissions hover around 40 gigatons, sequestering that much through a single, monetizable industrial sector is a massive structural dent.
It is.
It proves that scaling CDR doesn't have to rely entirely on government subsidies for geologic storage. It can be driven by the raw market demand for better energy storage materials.
If we connect this to the bigger picture, this study validates a crucial pivot in climate strategy.
A pivot from pure disposal to utilization.
Exactly. It proves that the EBPM pyrolysis route is the economically viable, energy-efficient path for bulk defossilization.
It's turning a problem into a product.
It models a realistic scenario where we leverage renewable energy and direct air capture, not just to mitigate harm, but to construct the materials of the future from the pollution of the past.
It is a brilliant blueprint for industrial ecology. But as we look at banking 2.57 gigatons of carbon annually into batteries and composites, we have to address the long-term reality of material life cycles.
This raises an important question, and it is one the source material touches on regarding the physical properties and permanence of the graphene itself.
The permanence of the vault, so to speak.
Right. For this to qualify as a permanent negative emission technology, the graphene must act as a stable, long-term carbon sink.
Does it?
The study points out that bottom-up graphene synthesized from methane via CVD or EBPM exhibits high chemical stability and resistance to degradation.
More so than older methods.
Significantly more so than older, top-down methods that yield heavily oxidized, fragile graphene.
But even highly stable carbon lattices are subject to entropy. Nothing we manufacture is entirely immune to environmental breakdown.
And that is the multi-generational variable we have to consider.
Right.
Even pristine graphene networks can eventually degrade over extended periods due to exposure to oxygen, ambient moisture, and specific biological decomposers in the soil or water.
So what happens centuries from now to the millions of tons of graphene-enhanced battery cathodes, building materials, and polymer composites?
That's exactly the issue. When those products eventually reach the absolute end of their usable life cycle and begin to break down, do they oxidize and release that stored carbon right back into the atmosphere as CO2?
It is a massive deferred waste management challenge.
It really is.
We might successfully pull gigatons of carbon out of the sky by 2050 to stabilize the immediate climate crisis, but we are effectively handing a complex containment problem to future engineers.
They will have to develop infinite recycling loops for these graphene materials.
Or figure out a way to permanently entomb them once their structural integrity fails, just to ensure that the carbon we captured today stays captured forever.
It forces us to realize that carbon management isn't just about the point of capture. It requires a permanent geological scale commitment to monitoring the materials we create.
It adds an entirely new layer of responsibility to material science. That's it for our deep dive into the techno-economic assessment of electricity-based graphene production from atmospheric carbon dioxide as a potential negative emission option.